Out of this, 50 marks are reserved for your lab sheet submission, 30 reserved for Viva. This is your lab sheet submission. This is your Viva Voci, and 20 marks for attendance. Now, I want the class representative of your section should send me the attendance sheet based on the, I think attendance sheet can be downloaded from the Google Meet itself. The person who is the administrator of this meeting, he can easily download the attendance sheet. So I want this attendance sheet should be sent to me after I finish the class. So suppose I finish the class at 8, by 8:10 I should receive the attendance sheet. Understood?
Okay.
So this is very important because 20 marks is reserved for the attendance. So the attendance is very mandatory for this this laboratory class. 30 marks Viva I will be taking after the experiments are over. Then 50 marks. There are 4 experiments. Accordingly, we can distribute the marks among the experiments. Okay. Now, all of you, since the class timing is from 7:30 p.m. in the evening, so all of you must join the session or join the Google Meet session by 7:25. Should not delay. Anyway, I can see that because once you send me the attendance sheet, I can see that who is joining late. So that from the attendance sheet, I can easily figure out. So that discipline I am expecting from you people to maintain. During this unprecedented situation of this COVID pandemic, it may not be possible, to have the offline class. So if people can visit the laboratory and there you can perform the experiments. Ideally, it should be the ideal case because from that you may have some physical understanding what exactly is happening. But during this unprecedented situation of COVID pandemic, it may not be possible for you people to visit. So virtually, people have to perform the experiment. So for this virtual experiments, some certain disciplines has to be maintained. Otherwise, if people may not understood that what is happening exactly, and maybe in the near future when you will be visiting the university, when you will be visiting the laboratory, you will get a feel, yes, I have done the experiment virtually, and this is the actual experimental setup that is available at the Hardelux laboratory. Is that clear to everybody?
Yes, sir.
Okay, fine. Now, today, no, not that is sufficient. That is sufficient. You can take the screenshot at the same time. You can also download. You just figure out. I've seen some of my past students used to send me the attendance sheet like that way only. Google can register when people are entering to the class and when you are leaving the class. So through the Google Meet, it can be done. Just figure out, explore it. Now, in this fluid mechanics class, I do not know because fluid mechanics 1 class, if people have performed or if people know that what do you exactly mean by Renoult experiment? It is one of the fundamental building block of fluid mechanics. Fluid mechanics is a subject because there have been several topics relating to the fluid mechanics, whether it is statics, whether it is dynamics, but the fundamental of building block of fluid mechanics is a Renoult experiment, and it was performed by Osborne Reynolds maybe 150 years back. But the experiment is still relevant today. Why its relevance is very important from the present perspective? Because it was the experiment through which one can typically understand how the fluid behaves under different situations. Whether the flow, if we increase the velocity, what will be the behavior of the fluid? Or if you reduce the velocity, what will be the behavior of the fluid? So the behavioral aspects of the fluid can be understood or can be figured out. We can easily figure out from the Renoult experiments perspective. Accordingly, one may essentially perform the experiment by making a simple laboratory setup, and that through the setup one may typically identify what is the corresponding consequences of fluid velocity on the physical aspects of fluid. So what do you mean by physical aspects? Physical aspects means if you know that say if a fluid which is flowing to a pipe or which is flowing to any media, why I should concentrate on pipe? I may concentrate on any media also. If it is flowing through any media, what will happen? Based on the velocity of the flow, fluid will behave differently in different medias. For example, say a fluid, suppose you have a obstacle like this, simple obstacles, and fluid is flowing over the obstacle. So what will be the corresponding behavior of the flow? What will happen? There will be a generation of vortices. These vortices will be generated past the obstacle, and these vortices are typically termed as the recirculation bubble or recirculation zone. Or in many cases, what will happen? Suppose there is a sharp corner. Suppose this is a sharp corner. This is a certain step, and fluid is flowing here like this. Now what will happen? There will be a creation of negative pressure here in this zone, and there will be a formation of this recirculation bubble, or sometimes it is called as eddies, formation of eddies. So these are the typical behaviors of the fluid, or the fluid may show this typical behavior based on the inlet velocity of the flow. So if the fluid is flowing a particular inlet velocity, the fluid generally displays this kind of behaviors based on the velocity of the flow. Or it may also happen that if the velocity is very less, this behavior may not exist at all. Simply fluid will behave like is a simple, potential flow kind of situation. I do not know whether you people have come across potential flow or not. It's something like this. It will come and it will show it is simply move like this. And this type of flow, when the fluid velocity is very less, we call Planck flow or Stokes flow when the velocity is very less. But when the velocity has some moderate velocity, it will have this kind of behavior due to the generation of negative pressure in this region. This is called recirculation zone. Now the question is whether this kind of behavior with fluid will automatically all the time the fluid will exhibit this kind of behavior. The answer is it depends on the fluid velocity. Which velocity it will give this kind of behavior? That is a typical question that was in the mind of fluid dynamics. So it was Osborne Reynolds who actually came up with some idea and performed some experiments, and through which he decided, or he actually demarcated two different regimes of fluid flow. One is laminar fluid flow and another is turbulent fluid flow. You already know what is the laminar and turbulent flow. Laminar flow, basically fluids are flowing in terms of layers. So one layer of fluid is flowing over the another layer. Fluids are flowing in terms of layer is called, that's why the name is laminar flow. Turbulent flow is something like that. The fluids are not flowing in terms of layer. There's a random motion in between the two layers. There's momentum exchange. One layer is getting momentum from the momentum from one layer, or packets of fluid particles is suppose its momentum is getting exchanged to the next layer or the layer above it. So there is a continuous momentum exchange of the layers of the fluid particles, which is basically moving through the layers, and there is a flow become turbulent. And what is the indication of turbulent flow? Indication of turbulent flow: formation of eddies, small scale eddies to large scale eddies. This kind of eddies. There are several forms of eddies. So if you see, there are several forms of eddies. Means eddies. So how the eddies forms? Eddies form basically the fluid particle breaks or layers are breaks and forming this kind of recirculation zone. And recirculation zone are basically terms of the eddies. So what will happen? These eddies are, when the fluid is flowing, these eddies are getting dissipated. That what is the dissipation mechanism? So suppose there is a big eddy and it is forming smaller eddies, and this smaller eddies is forming further smaller eddies. And this type of typical dissipation that one may observe when the flow is fully turbulent is called the energy cascading. Energy cascade. Energy cascade means the one energy is getting cascaded between the smaller eddies or smaller recirculation zones. It's called energy cascade, which is basically prevalent in the turbulent flow. Now, again, the question is, we know these concepts and how the concept is known. People perform a series of experiments on the fluid mechanics. Those are, scientists, researchers, industrialists, industrial R&D people. Those are working in industry. They perform a series of experiments and try to understand this concept. What is actually happening when the fluid is flowing to a pipe? What is exactly happening? Is it really always being laminar all the time, or this kind of typical phenomena one may observe when the flow velocity is very high? Then this phenomena later on, further exploited by the modern fluid dynamics and perform several calculations, analytical calculations, numerical calculations through computational fluid dynamics techniques, then experimentations. So this kind of energy cascading that is observed in turbulent flow, laminar flow, there is no such disturbance. Fluid is flowing in terms of layer. One layer is moving above the another layer. Then what he actually did, Renoult, what he actually did, he performed an experiment. So there's a long pipe, and the pipe already people know. There's a bell mount entry. Bell mount entry means there's the entry through which the dye is injected. So fluid is flowing to this pipe in this direction, and the dye is injected from this bell mount entry. The dye is moving like this, and fluid is flowing like this. Now what he did actually, there is a tap which is attached here, and he actually suddenly started closing the tap. So initially the tap was completely tight, and he suddenly started releasing the tap. If you release the tap, then what will happen? Fluid velocity will keep on increasing. So for a particular volumetric flow rate Q1, he found that the dye is remaining like this. But when he started just releasing the tap, what will happen? A particular volume rate Q2, he found that there is a fluctuation in the dye. Dye is getting fluctuated. So then he said, yes, that means there is a transition is happening in the fluid flow. A particular volumetric Q3, so he found that there is a typical fluctuation is observed in the dye. Then he actually keep on releasing this tap, and found at a particular volumetric flow rate Q3, there is a complete mixing of the dye throughout the entire domain. There's a complete mixing of the dye through the entire domain. Then he determined that when the fluctuation occurred, the flow is laminar. But when the fluctuation started occurring, there is a random motion which is observed due to the motion of the dye, and there is a complete mixing of the dye with the total fluid which is remaining inside the pipe. And he told that this is the condition when the fluid is turbulent. So accordingly, he introduced a number, but later on the number was named by him. He introduced a number, it's called a Renoult number. Already you know Renoult number, it is a density, and he said that this is the situation when the Renoult number, he calculated like this: density rho into velocity of the fluid and diameter of the pipe, that is the length scale of the pipe, by mu. And he calculated this value. He found that when the Renoult number is less than say 2000, but this is not the actual figure. Actual figure is the 2060. But for your case, for your fundamental and since you have a preliminary background, so around when the Renoult number around 2000, he actually found that there is no such random motion. But when a Reynolds number is greater than 2000, he found that the flow is completely turbulent. So he characterized the situation, laminar to turbulent transition, up to which value of Reynolds number flow will be laminar, and beyond which value of Reynolds number flow will be turbulent. So then he introduced this number for characterizing the flow, whether it is a laminar flow or whether it is a turbulent flow, based on the typical fluid properties, density, viscosity, velocity of the flow, that is the inlet parameter, and geometrical dimension of d, and calculate this value of Reynolds number. So this is the typical experiment he performed, and accordingly he calculated the Reynolds number and also introduced the concept of laminar and turbulent transition of the flow that is happening when the fluid is flowing through a pipe. Now the question is, maybe I can throw these questions to you people. I think I do not know whether I have discussed this in the class. I don't know. Some of you may have attended my class in fluid mechanics 1. That this Reynolds number 2000 is this a universal value, that when all the cases Reynolds number less than 2000 the fluid will be laminar, and all the cases when the greater than 2000 the fluid will be turbulent? Yes. Some of you are trying to answer this question. Shahid, yes.
No, sir, it is not a universal value. It depends.
Why?
So it depends upon the. It depends upon the condition, like what we are taking. Like for the pipe, it is 2000. But if we change the material and all those things, then the Reynolds number changes.
Material means?
So like if it is sir.
Your answer is correct, but your explanation is wrong actually.
Yes,
Your answer is correct. You are not able to explain it properly. What about others? If I use oil, if the oil is flowing to a pipe, the same thing will happen, right? We are typically interested in this ratio. The same thing will happen, right?
Sir, it may basically depend upon many other factors. Like we had a graph when we studied flow through pipes and all, like relative roughness and friction factors. So it depends.
Oh, you're going. Yeah, that is true. But I'm asking that whether this is a universal. Yes, answer is definitely right that this is not a universal thing. That all the time when it is of 2000, it will be laminar, and greater than 2000 it will be like turbulent. It's not like that. But this concept you should know actually. Your answer is correct, but the concept behind this phenomena you should know. But let me explain, because you people are just trying to answer this question. You just may think of, but I think that I have explained in the class. I don't know, but again I am explaining to you people. Please remember, this value of Reynolds number, which is less than 2000, it is laminar, and greater than 2000 is turbulent. It is only for the flow through a pipe. The laminar and turbulent transition, the value of Reynolds number less than or greater than 2000, it is only for the flow through a pipe, not for any other cases. Why? Answer is, it depends. One of the important parameter of this system is the geometrical dimension d. How and why? Suppose let us say there is a obstacle. I just simply explaining, and the fluid is flowing over it. Then in this case also, that Reynolds number greater than less than 2000 fluid will be laminar, and greater than 2000 fluid will be turbulent. Is that so? No. Why? Because Reynolds number here a characteristic length scale, let's say d is the diameter of the cylinder, rho v d by nu again. In this case, for the flow over a circular cylinder or flow over a square cylinder or any obstacle like this, cylindrical shape, when the Reynolds number is greater than say 180, flow is turbulent. Is less than 180, flow is laminar. Another example? Yes, we have got another example. What is that example? You already know that. Flow over a flat plate. This is a flat plate. Boundary layer theory you people have studied, right? Flow over a yes or no?
Yes,
Yes,
sir.
yes, sir.
Sir, even
Yes,
plain
sir.
Poisson flow.
Yes also, right. Flow over a flat plate. What will happen? There will be development of boundary layer like this. This is the plate. This is the leading edge. This is the development of boundary layer. Yes?
Yes,
Yes,
sir.
sir.
Yes, sir. Yes.
For this situation, when Reynolds number is greater than 2 into 10 to the power 5, flow is turbulent. When Reynolds number is less than 2 into 10 to the power 5, flow is laminar. Why? Because the geometrical dimension depends upon the free stream length from the tip of the plate. We are measuring that length like this. And this is the situation for the flow over a flat plate or boundary layer flow. This is a condition that has to be satisfied when there is a transition to turbulence or when there is a laminar flow. This is a complete laminar flow. This is completely transition to turbulence, or sometimes called turbulent flow itself. For you, since you are in a preliminary understanding, you can call it turbulent. But those who are studying the advanced fluid mechanics, you should say the transition to turbulence phenomena started to occur. How for your understanding, I can tell you this is an important question. May not be relevant for you now, but you should know these physical consequences. Turbulent situation or transition to turbulence generally appears in the form of turbulent structures or three-dimensionality in the flow. Flow becomes three-dimensional. Please always remember, when the fluid is laminar, flow is always two-dimensional. But when the flow is turbulent, flow is never two-dimensional. There should be a three-dimensional appearance of the three-dimensional structures. How it appears? In the form of sticks or pluffs, or sometimes it's called this kind of structures. Puffs or sometimes plugs, this kind of stuff. So that means if you start measuring a signal, suppose what you can do, this is a typical boundary flow. Suppose you are experimentalist, and what you can do, suppose you just probe a hot wire anemometer. You know what is a hot wire anemometer? Somebody should know what is a hot wire anemometer. Hot wire anemometer. Hot wire anemometer is a device through which you can calculate the velocity in any places in the flow domain. Suppose you have put a hot air anemometer, and what you can do, you just measuring the signal with the time. So fluid is flowing. You have placed a hot air anemometer in this location. Then you are measuring the signal with the time. So how to show here? I can show. Suppose you have put a hot air anemometer, and this is the signal with respect to time. Signal means velocity signal. This is the time. So then what will happen if the flow is laminar? Then it will show a periodicity in the flow. Periodicity means completely periodic. This kind of flow it will show. This kind of signal, velocity signals behave this kind of periodicity. But as soon as the flow is turbulent, it will not be periodic. It's something like this. Random fluctuation in the flow will appear. So random fluctuation basically are the consequences of three-dimensionality that may appear in the flow domain due to the presence of turbulent structures that one may observe in the flow domain. Anyway, I think you should know this concept. So in your experiment, that this fluid mechanics experiment, that is called Renoult experiment, and the friction factor already you know, again positive flow form equation, what you will be performing? You will be performing a pipe flow experiment, something like that. So if you can come in your near future, if you may happen to visit our hydraulics laboratory, here this is the Renoult apparatus. You can see the Renoult apparatus. This is our staff who is working on the Renoult apparatus. So here you can see this is the chamber through which this is a small chamber. Here these are things here written. Here the water is flown and dye is injected, and the injected dye initially it will be behaving like this, and as soon as the turbulent scenario occurs in the flow domain, dye will start fluctuating, and the entire pipe will be filled up with a red color. So initially here actually we are injecting a red dye, and the red dye will be completely filled up throughout the entire pipe. So here in our laboratory you will be performing this kind of that is virtually you will be performing this kind of experiments. And this experiment, this is the bell mount entry. Already I was explaining what is the bell mount entry, and the bell mount entry basically we are injecting the dye, and we just increasing the flow rate by just changing the tap outlet which is basically mounted at the outlet of this pipe. And accordingly you can see what is the typical fluctuation one may observe, and on the fluctuation observed you can calculate this is the transition, that the transition is happening. So in your lab sheet that you will be performing, so this is the typical lab sheet that you can see here. This is a lab sheet. Here I will be sharing this lab sheet with all of your people. So here you will be filling up this this data sheet. Data sheet is perfectly filled up, because that means we are expecting that you people have performed the perform the experiments in the laboratory, and accordingly you have filled up this data sheet based on the experiments that you may perform or you will be performing, or that already you have performed in experiments in the laboratory. According to this, the flow rate one may obtain. So based on this lab sheet, data available in the lab sheet, you have to fill up this data and calculate the Reynolds number. Once you calculate the Reynolds number, you can see the straight line means there is a completely laminar region, wave means transition, diffuse means is completely turbulent region. So this is a region you need to identify once by calculating the value available in this data sheet. And once it is done, then you have to plot there is a scale called IK V to the power n. This is not coming properly in my PC because I don't know, but it will come basically because I'm using my Linux PC, that's why it is not showing properly. Accordingly, you can calculate this I value, and finally you have to plot in a log scale I versus V. From this information available in the data sheet, and you have to calculate the N and K for laminar and turbulent flow situation. That is how to calculate N and K. So N and K, once you plot the graph like this, it will be showing different slope, and N can be calculated from the formula already given here, laminar formula, and N1 turbulent region. This will be formula given in this data sheet, lab sheet available. Once it is done, then you have to calculate the friction factor. Friction factor already you know from the Hagen-Poiseuille's equation, that is friction factor 64 by RE, and from that this is the situation on the laminar flow, and for the turbulent flow, again you have to calculate the friction factor. That is, you have to calculate the friction factor both for laminar and turbulent flow. Laminar flow 64 by Barry, already you know from your analytical understanding that when you perform the Hagen-Poiseuille's flow equations, then 65 RE, and for the turbulent cases, this friction factor is 0.3164 by RE to the power 1 by 4. How it is coming? If you may recall, when you have performed when you have studied the boundary layer theory, there is a what is the boundary layer equation when it was derived? That is something like this: F triple prime plus half F double prime into F equal to 0. F is basically your del y, del eta del y. Right, this is a thing actually you have done in your boundary layer equation. And there is a person, it's called Blasius. Blasius, basically he was the PhD student of Osborne Reynolds. He did his PhD under Reynolds. So Blasius basically, no, sorry, I'm extremely sorry. Blasius did his PhD under Prandtl. The boundary layer theory was given by the Prandtl. Prandtl's student was Blasius. So when the Blasius did his PhD under Prandtl, actually he solved this equation. It was his PhD thesis when he was performing a PhD, when doing PhD under Prandtl. So this Prandtl actually, when he solved this equation analytically, he calculated the friction factor like this. That friction factor should be F equal to 0.3164 by RE to the power 1 by 4. This is an analytical calculation obtained from the Blasius boundary layer solution. So here you can calculate the friction factor. Accordingly, you just fill up this chart and see how much value you are coming, and whether laminar flow which value friction factor is getting, and turbulent flow what value friction factor are getting, and accordingly you have to plot it, friction factor versus P versus I, and friction factor versus Reynolds number for different cases. That's it for this experiment as far as the experiment is concerned. characteristics of pipe flow experiments. There's a Reynolds experiment followed by the calculation of friction factor. One is by Hagen-Poiseuille flow equation, another is by equation given by the Blasius from his boundary layer theory solutions. So what I'll be doing, I'll be sharing this folder. Here actually in the folder there are certain videos are available. So you can see this is a video, though I don't know quality is not up to the mark. So some videos are available here. So you just go to the video. I can share this folder with your class representative. The class representative can download this folder. You can share with among your fellow batchmates. So here you can see there are lots of videos are available. So you can go to the video. You can see what type of what is the typical experiment one can see for this Reynolds experiment kind of scenario. Or this is the video. These videos are recorded in our hydraulics laboratory of our mechanical engineering department, and you can go to the video. You can see, you can have a proper understanding how the situation when the fluid is changing its behavior from laminar to turbulent flow kind of situation. This is all about your pipe flow and hydraulics, pipe flow and friction factor experiment. And here data sheet you have to perform, you have to fill up, and accordingly you have to see the videos. Or some of you may be interested to further understand. So you can in when the laboratory opens, when the university opens, so you can visit our laboratory. You can see the experimental setup and also the you can tally that experiment that is being done, and that is also available in our hydraulics laboratory. This is all about your experiment. And there are certain YouTube videos are also available. So you just download, see the YouTube video. I can show you one video here. So this is the see for example Reynolds experiment. Reynolds experiment. Yeah, Reynolds experiment. Yes, there are a lot of this is the experiment. You can see Reynolds experiment here. See, this is the kind of situation. Flow is flowing here. Typical laminar flow situation. When the velocity is increased, there will be formation of waves or the dye. This is a pink dye. Pink dye will start fluctuating. It will show the transition to turbulence or turbulent nature of the flow. It will definitely show. And now you can typically appreciate. Yes, exactly. This is the pipe. You can see the perplex pipe through which you can see the dye. This is the pipe. You see the fluctuation. Increase the velocity and started fluctuating. You can see complete mixing. Complete mixing means flow is completely turbulent. So here you can typically observe typical laminar flow, straight dye motion. Dye is moving straight in a straight line. There is no fluctuation happening. Now fluctuation is happening. Why? Velocity is increased. Now the complete mixing. Complete mixing means flow is completely turbulent. So then you can typically appreciate this is a situation one may observe for the turbulent flow. There is a complete randomness in the flow. Already it is written in the animation itself. Here also another animation is given. This is a laminar flow. I don't know it can be visualized or not. Yes, it can be visualized. And you can Reynolds number and some certain concepts. So already you know this concept. So this is a laminar flow. And then velocity is increased. You can see small fluctuation is appearing in the dye itself. Now the velocity is further increased. There is a random fluctuation and complete mixing of the dye in the fluid, which is see the random fluctuation. So this is the exact experiment you people would be performing, or you people may see that is the apparatus available in our laboratory. Okay. Any other questions from any of you? This is all about my
Yes, sir.
yeah.
Sir, in the table you showed us for the experimental data collection, I saw a time column. Sir, why do we need a stopwatch for this
Okay.
experiment?
Stopwatch basically you have to calculate the velocity. How you calculate the velocity? Because velocity we don't have a hot air anemometer available. So how much fluid is you have got for a particular time, 15 minutes. Then there is a volume of fluid you have obtained. Once you know the volume of fluid obtained, so accordingly calculate the flow rate, Q, volume by time, or you can calculate the velocity automatically. You know diameter of the pipe. That's why this is required. Understood? Had we, if you have hot air anemometer, you can easily calculate the velocity. But hot air anemometer facility is not available in the Reynolds experiment. Or the person when Reynolds did the experiment, that time water anemometer was not available. The only option is you know the volume of fluid which is coming at a particular time t, so from which you can calculate the velocity of the flow. Understood? It's a very simple
Okay, sir.
concept. You can just go through the chart, you will understand everything. There are no rocket science behind this.
And sir, we have always witnessed, most generally witnessed transition from laminar to turbulent flow. Sir, we can do the other way around. Can we do the other way around from turbulent to laminar flow?
Have you studied thermodynamic irreversibilities?
Yes, sir, we have studied. Sir,
What
actually,
is
the
it?
video you showed us, in that I saw that initially the duct was wide and a little bit wide. Then it went on constricting, went on getting
No.
narrower.
That is different. That is different.
Okay,
That
sir.
is different video. It is not related to that. Is they are trying to explain the Reynolds number concept.
Okay.
That is called thermodynamic irreversibility. Nothing can be, when turbulence is a form of thermodynamic irreversibilities. It cannot be brought back. Then it will violate the second law of thermodynamics.
Yes, sir, we had it in our last semester.
Yes. It will violate it. Not possible. Suppose if you prepare say puffed rice, puffed rice. What is puffed rice?
Yes, sir.
Can it be brought back to rice again?
No, sir.
So that is irreversibilities. Understood? Turbulence is a form of irreversibility. It cannot be made laminar. But you can reduce the tubular intensity by performing some kind of action. But flow cannot be, made laminar or become turbulent. But there is an advanced concept. It's called relaminarization. That is beyond the scope of your syllabus. But if you are interested, I can tell you. Relaminarization means that near to the wall, suppose the fluid is flowing, there is a famous scientist, Professor Narasimhan, I guess. He's now in some university in US. I forgotten which university. So he introduced the concept of relaminarization. What is relaminarization? That is flow when the fluid is flowing. Suppose this is the wall, and fluid is flowing over it, and what will happen? Very near to the wall, turbulent flow shows some laminar characteristics. Or there is a relaminarization. A turbulent flow will behave as if it is a laminar flow. That's called relaminarization. And what is the physics behind it? What is the concept behind it? If I explain it, you may not understand. There is a called dissipation of energy and dissipation of turbulent areas, and that dissipation causes the flow to behave in a laminar way. But that is restricted to a very narrow region near to the wall. Okay. So if you are further try to understand this concept, just you are welcome to discuss with me, or just type relaminarization.
So if the flow is completely turbulent and suddenly I constrict the flow passes to very small, I reduce the length, the characteristic length. So even then the flow will not become laminar.
No, it will not become laminar. It will be further. Velocity will increase. It will further be turbulent.
Oh.
See this paper. If you are interested, this paper you may download it. Professor K.R. Srinivasan. Previously he was in ISC Bangalore. Now he's in some university in the United States. So K.R. Srinivasan is a very famous scientist in fluid mechanics. So both of them are very pioneers in fluid. Professor Rotom Narasimha and Professor K.R. Srinivasan. They are a pioneer people in fluid dynamics fraternity. So this paper you can, if you are interested, you can read this paper. But I doubt if people hardly understand this paper, because it requires some fundamental, advanced understanding in the fluid mechanics. Then you can understand this concept, relamination of the fluid flow.
Okay, sir.
Anyway. So any questions from any one of you? Okay, fine. So I can share this folder with whom? Who is this class representative of?
So I'm handling the
Shahil,
yes.
Right?
Yes, I'm handling your subject. Yes.
Okay, Shahil. Just share me your email ID through WhatsApp, and accordingly I can immediately share this folder to you, and you can share this folder among your fellow batchmates.
Okay, sir.
And now is 8:15. By 8:20, you should send me the attendance sheet for today's class.
Okay, sir. So I'm sending the screenshots of the people of the people.
Screenshot
present.
is, yeah, but attendance sheet you just try to explore and see how it can be.
Yes, sir. Yes, sir.
shared.
I'll do that from the next class. Okay.
Okay, fine. Okay then.
Sir, can I tell
Yeah.
you something?
Yes.
Yes, sir. My name is Mulson Kanmoga, but there is short form M.K. So M.K mean my Mulson Kanmoga.
Okay. Okay. Fine.
Okay.
Fine. Understood. Understood, Mulsan. Don't have to worry. It is understood.
Okay.
Okay. Okay then. So okay. No. Wait. I want the lab sheet to be submitted by today is 20th January, right?
Yes, sir.
By 31st January
Okay, sir.
to Google Form, or you want you require more time? No printing. Only soft copy, PDF, and the uploaded in the Google Form. I will circulate the Google Form in the group. Google Form? You don't know Google Form? Google Form I will be generating. This is you have to calculate the value. You have to put your comments. Do not copy. Put your comments and make a graph. Attach it here. Write your name. Fill up this form completely and make a PDF and submit. That's it.
Okay, sir.
Fine. So I by 31st January. Okay.
Okay.
Okay. Okay then. Thank you.
Okay, sir.
Thank you, sir.
Okay.
you, sir.
Okay.
Thank you, sir.
Okay.